Today we're going to look at something called VSEPR Theory. And VSEPR is an acronym, and it stands for Valence Shell Electron Pair Repulsion. And what that means is that the valence shell electrons, that means the electrons on the outside of the atom, all repel each other. So if you have a molecule with more than one atom, all those atoms kind of repel each other because the outsides of them are made of electrons that all try to get away from each other as much as they can. So we can look at the shapes of small molecules and figure out what their shapes will be based on how many electron clouds are around them. So let's start with the simplest one, which is linear. Now obviously if you only have two atoms, the only thing that can happen is it's going to be linear. But if you have more atoms than that, it's going to take a linear shape if you have two electron clouds, because the farthest away they can get from each other would be 180 degrees apart. So think of this. Think of this as our central atom. And then think of this as a bond to another atom, and this as a bond to another atom. And those bonds, remember, are shared pairs of electrons, so that's like an electron cloud. And these two electron clouds want to get as far away from each other as they can, so what they're going to do is go to the opposite sides. And so we might have another here, another one like that. So that will take a linear shape. So that's going to happen anytime an atom only has two bonds. Now if it had something like this, double bond, that's still going to take a linear shape because the double bond shares 4 electrons, but it doesn't matter because it's still a 1 electron cloud. And if I made, let's say, that a single bond and that a double bond, or this a single bond and this a triple bond, it's all going to work the same way because we have 2 electron clouds and they're trying to get as far away from each other as they can, and that's going to make a linear shape. So we have a couple good examples of that. Would be carbon dioxide. You'd have to go back and review your Lewis dot formulas, but if you did that, you would find that carbon dioxide looks like this. So around the carbon, we've got 2 electron clouds. Another really common example of this is beryllium hydride. Now beryllium has only 2 valence electrons, and it ends up sharing both of those and making 2 bonds. So we have just 2 electron clouds around that also. And the next simplest one is called trigonal planar. And that happens if you have 3 electron clouds, which honestly isn't all that common. Mostly it happens when we have boron in the middle, because boron does not follow the octet rule, and boron likes to make just 3 bonds. So it ends up with only 6 electrons around it, and for some reason boron's perfectly happy with that. So that happens with boron. It sometimes happens if the central atom might have maybe a couple of single bonds and a double bond. That happens with carbon sometimes. It might have a couple single bonds and then 1 double bond. But anyway, anytime you end up with a molecule that has only 3 electron clouds, the furthest that they can get away from each other is to form something like this. So we might have a central atom with 3 outer atoms, and they're going to do that. And that's going to be planar, all in one plane, and they're going to be separated by about 120 degrees, where this would be like 180 degrees. And if you remember your geometry, you won't have any trouble with those two anyway. So this is going to happen when boron, let's say, bonds to hydrogen, or it could bond to fluorine or chlorine or some combination of those, but anyway, boron's going to have 3 electron clouds around it. So those are the first 2. There are 3 more shapes that we'll learn this year. There are plenty of more shapes, but we only do 5 the first year of chemistry. So these 3 shapes are all going to have something in common, and that is that they're all going to have 4 electron clouds, but some of those electron clouds are sometimes going to be unshared pairs of electrons. So let's start with the one that shares everything, and this is called tetrahedral. Now, one might think that if there's going to be 4 electron clouds, you might get a 90-degree bond angle, and that would work if it was going to be a planar molecule. But there's actually a way that these electron clouds can get even further apart than 90 degrees, and that is if they start going in 3 dimensions. So it's very hard to draw this. We will do models in class and you'll see it a little bit better. But it's something like this. This is my central atom. And I will be asking you to draw this, so this is a little art lesson for you. Let's say that this is carbon, because this happens a lot with carbon. Carbon always likes to form 4 bonds. Silicon would do that too. So we would make a little dimple over here and draw a line out here, a little dimple there, and draw a line out there. And then we could put anything we wanted there. Today we'll just put hydrogens, but you could really bond it to anything. You could put chlorines or fluorines or whatever on that. But let's put hydrogens there. And then we have this and this. Now, this is supposed to look like these two are coming slightly out of the board at you, and those two are going slightly back into the board at you. And the bond angle there is 109.5 degrees, and that's a perfect tetrahedron. Now, molecules that don't have all the same atoms here might shift that a little bit, and the angles might be a little bit different from each other. If the atoms are different, the angles might be different. But if you have 4 hydrogens or 4 chlorines or 4 whatever, they will be the same, and they'll be 109.5 degree bond angle. So that is tetrahedral. Now the other two are kind of variations on that theme. So let's do bent next. And this happens when instead of a couple of these bonds, we have unshared pairs of electrons. So if you think of something like oxygen and sulfur, you might remember that both of those have 6 valence electrons, and they want to get 8, and so they will share to get 2 more. That means there's going to be 2 bonds, but then they also have those 2 unshared pairs of electrons. So let's just use water because that's a nice simple example. And this again is going to end up being a planar molecule, even though the unshared pairs of electrons are not in the plane necessarily. So here's our oxygen, and it has 2 unshared pairs of electrons that we can just draw like that. But in reality, maybe one of those pairs is out from the board and one of those pairs is back in the board. So it really kind of takes this same shape, except that we only think about the 3 atoms, and that's why we call it bent, even though if you thought about all of the electron clouds, it would be more like tetrahedral. Now, the interesting thing about this is that this is larger, this being that electron cloud, the unshared pairs, is larger than a shared pair. So what that means is that these are going to kind of push, they're going to take up more than their fair share of space, and they're going to push these a little bit closer together. So this bond angle is only 105 degrees. So it's a little bit smaller than that idealized tetrahedral bond angle. Now lastly, we can have something called a pyramidal shape. I'll just erase this. Put it up here. And that might happen if you had something like nitrogen, for example. Now this needs to be drawn like a little 3-legged stool. So that's what you need to picture, a 3-legged stool. And the reason that that happens is because we have this unshared pair of electrons there. So really, it's a variation on this theme of tetrahedral, except that these 3 are atoms and that isn't. And so if you think of a little 3-legged stool arrangement, maybe you can see how we end up getting a pyramidal name for that. So again, this takes up more room than any of those bonds, and that's going to push these a little bit closer together than they would be otherwise. And so the bond angle here is 107 degrees. So those are the different types of shapes that you can get. And again, there are more, but those are the only ones that we're going to learn about this year. And you will be taking other molecules and looking at them, and the best way to approach these kind of problems is to draw out the Lewis dot structure so you can see what you've got. How many bonds do I have? How many unshared pairs do I have? And what does that match up with in terms of the examples that we've done here?